Welcome to U6L2 Quadrilaterals. So this is going to be a condensed version of quadrilaterals. We're going to talk about some of the main properties of different types of quadrilaterals, and we're going to go over some questions that use the properties of quadrilaterals, okay? So first of all, really important, a quadrilateral is any four-sided figure, okay? So a four-sided polygon is a quadrilateral. Now, there's only one relationship that we're going to ever need to be able to use, or that you can use rather, when you're talking about a generic quadrilateral without any additional information. And that is that the interior angles have a sum of 360 degrees. So if I call these interior angles A, B, C, D, right, respectively, based on their vertices, then when I add those four angles, I have to get 360 degrees. And that is a relationship that you can use anytime it's a quadrilateral, even if you don't know any other information about the angles, the sides, anything else. Okay. All right, continuing on. So a trapezoid. So a trapezoid is a special type of quadrilateral, such that it has at least one pair of parallel sides. Okay. It has one pair of parallel sides. It can't have two, but generally we call that a parallelogram. Okay. But it has to have at least one pair of parallel sides. So in this case, the pair of parallel sides are going to be AB is parallel to DC. Okay. You can't assume it. You have to know which ones are parallel. But those are the ones that I'm telling you are parallel for our purposes. Okay. So the adjacent angles between the parallel lines are supplementary. That is a very important relationship that you can use for trapezoids and additionally for anything else on this page, because everything else on this page is considered a special type of trapezoid, right? And you'll see what I mean as we go down. But anytime you know that there is at least one pair of parallel sides, then you know there are at least two pairs, okay, of angles that are supplementary. So in this case, A and D, which are between the parallel lines, are supplementary. So A plus D is going to equal 180. And the same for B and C, which are also between the parallel lines. Okay, it's not true for A and B, for example, since we do not know that A, D, and B, C are parallel. So it only works for the angles that are adjacent between the parallel lines. All right, continuing on. So a parallelogram is also a quadrilateral. Technically, it's also a trapezoid. Okay, so this is also a trapezoid. So a parallelogram is actually a special trapezoid. I'm going to go ahead and just add that in here just for clarification, with exactly two pairs of parallel sides. So it has to have exactly two pairs of parallel sides. For our purposes, let's go ahead and label these. So AB will put one arrow and DC one. So those are parallel. Same thing for DA. So we'll put two and BC as well. Okay. It's going to be hard to label everything for a parallelogram because there is so much information, but I'm going to do my best. So two pairs of parallel sides by definition is a parallelogram, and it's a special type of trapezoid. So a couple more things that are also true. The opposite sides are not just parallel, they're also congruent. And the opposite angles are congruent as well. Okay, so the opposite sides are congruent and the opposite angles are congruent. Okay, so for the opposite sides to be congruent, I'll go ahead and add these little tick marks. So we have 1 and then 2 and 2. The opposite angles are congruent, so D and B are congruent. Same with A and C. And then another special relationship that works for a parallelogram, not a trapezoid and not just a general quadrilateral, is that the diagonals bisect one another. So the diagonals are going to bisect one another. That means that when I draw one diagonal and then I draw the other diagonal, they cut each other in half. Okay, so they cut each other in half. Now, they don't cut each other. They're not the same necessarily, right? So what I mean by that is like this half is not necessarily equal to the half of the other diagonal, right? But the two halves of the same diagonal are equal to each other because they are bisected. Perfect. Okay, moving on. So now we have a rectangle, which is a special kind of parallelogram, which also has the properties of a trapezoid, okay, and the properties of a generic quadrilateral. So as we go down, it's almost like a flow chart. So keep in mind, everything that happens above applies to this as well. So a rectangle is a parallelogram with 4 right angles. So it has 4 right angles. So not just one, it has all 4. So all 4 of these are right angles. And then its diagonals, so here's another important property, okay? Its diagonals bisect one another just like we have up here for parallelogram, but they're also congruent. Okay, but they're not necessarily perpendicular. So keep that in mind. Okay, so if I draw in these diagonals, they're actually congruent to one another. So what that means is they bisect each other and they're congruent. So all 4 of these lengths, okay, from like the center basically of my rectangle more or less, from this point where they bisect, that distance from there to each vertex is actually the same, okay? And the diagonals themselves are the same length. Okay, but these angles in here are not necessarily right angles here. Okay. Perfect. Moving on. So a rhombus is a parallelogram with 4 congruent sides. So a rhombus has all the properties of a parallelogram, which has the properties of a trapezoid, which has the properties of a quadrilateral. All right, so a rhombus has all the properties of all those up there. Additionally, it has 4 congruent sides. So what that means is that all the sides are the exact same length. It's almost like a square that's been pushed over. Okay? And the diagonals in this case are perpendicular, but they're not necessarily congruent. So when I draw in these diagonals here, they're not necessarily the same length, okay, even though they do bisect one another, okay, same properties as with parallelograms. But the new important thing is that these are right angles, okay? They are perpendicular to one another, okay? So not necessarily the same length, even though they do bisect each other, okay? So it's like a parallelogram that's special because all of the sides are the same, right? And then this angle here in the center is a right angle. Perfect. Okay, last but not least, a square. Without a doubt, it has the most properties of any quadrilateral. So a square is a rectangle, which is a parallelogram, which is a trapezoid, which is a quadrilateral, right? So it has every single property from above, but additionally, it has 4 congruent sides, okay? And since it's a rectangle, it has 4 right angles. So basically, we have a special version of a rectangle that has congruent sides. And then the diagonals for a square are not only congruent, but they're also perpendicular. Okay, so let's draw that in. So if we draw in these diagonals for a square, let me fix that. If we draw in these diagonals for a square, not only are they congruent, but they're perpendicular. So meaning that all of these lengths from that point where they intersect here in the middle to the vertices are all the same. Same as with a rectangle, okay? But then also that angle, just like with the rhombus in the center, is a right angle. Okay, and that's going to be very important that you understand that these angles are right angles because that's going to come into play with a lot of questions that we work on with squares and with a square and a rhombus. All right, moving on. So now we can actually work out the questions. Okay, so it says example 1. In the diagram of parallelogram ABCD shown below, measure angle A is 5 times measure angle D. What is the degree measure of angle A? Okay, so let's figure out how to begin this. First of all, the diagram is of a parallelogram. Okay, and then it talks about angles. So what do we know about parallelograms and angles? Let's look. So what we know about parallelograms and angles is a couple different things. Okay, so if it's a parallelogram, we know the opposite angles are congruent, so that may be helpful. What we also know, because we can go up here, is that the adjacent angles between the parallel lines are supplementary. And then what we also may need is that the angles have a sum, if I add all 4 of them, of 360. So there's actually 3 different things that we could use, okay? I'm going to underline them there and point them out. And we just got to see what will actually help us. So let's see. So in the diagram, measure angle A. So angle A is this angle here at the top. This angle is 5 times measure of angle D. So I'm just going to call these A and D just to make it easy. The measure of angle A is 5 times the measure of angle D. So A equals 5 times D is basically what it's telling me, right? Okay, but this is a parallelogram. So these opposite sides are parallel. Okay, that means that these angles here, A and D, are between those 2 parallel lines, and they are in a parallelogram, which is also considered it's a certain type of trapezoid, right? So we know that those are supplementary. Okay, and I think that that's what's going to help us here. We're not concerned with opposite angles, like we don't care about A and C, for example, so we're not going to use that. And we're only talking about 2 of the 4 angles, so we don't care about these 2 at all. So the 360 is not going to help us because we don't care about the other 2 right now. So the only one that's going to help us is the fact that those are supplementary. So that means that A plus D is equal to 180. And ignore the degrees for a second just to make the equations more simple. But we know A is also equal to 5D. So we're going to substitute that in. So 5D plus D is equal to 180. Add like terms, 5D plus another D is 6D is equal to 180. And then if we divide by 6, we will get that the measure of angle D is 30. Say, or in this case, 30 degrees because we're talking about angles, right? So we know what that is, but the question that it asks us for is the degree measure of angle A. So what we really want is this guy. But that's easy enough, right? Because we know the relationship between angle A and angle D. We know that angle A is 5 times angle D. So all I have to do is take that value of D and now plug it back in. Okay, plug it back in. So we have that A equals 5 times 30 degrees. And so we end up with A is equal to 150 degrees. We'll write it with our correct notation. So you can either write it in words like the degree measure of angle A like here, or you can write it with the shorthand, which is this, measure angle A. Okay, so I'm just going to write the shorthand. So measure angle A, so bringing that down there, is equal to 150 degrees, and that's it. Okay. So next one, so example 2, in rhombus, HIJK, HJ is 10 inches long and IK is 24 inches long. What is the length of HK? Okay, so first of all, what are we talking about? What shape? Okay, so we're talking about a rhombus. So this is a rhombus. We know some things about a rhombus, and we're looking for, let's look at what we're looking for first to see what properties we need to look at. So we're looking at HJ, IK, and HK, and we're talking about their lengths. So HJ is a diagonal, IK is a diagonal, and HK is one of the sides of the rhombus, okay? So let's see any relationships that we know about those things. Okay, so let's look. So in a rhombus, the diagonals are perpendicular, but they're not congruent. But because it's a parallelogram, right, we know the diagonals bisect one another. So we know the diagonals bisect one another. We also know that the diagonals are perpendicular. And of course, all the 4 sides are the same. Okay, so let's go ahead and label some of that stuff on our picture. So all 4 sides are the same. So we know all 4 of these are the same. We know there's a right angle here in the middle, and it actually has it this time for us. But no matter what, we could put it. And then the diagonals bisect each other. So what that tells me, for example, is if I have HJ is 10 inches long, so if I know that this whole thing is 10 inches long, then I know that each half is half of 10. So I know that each part is 5 inches, right? Well, the same is true for IK. So IK here, that whole thing is 24 inches long, according to what it told us. But that means that each half is half of 24. So 12 inches and 12 inches. And again, that's because a rhombus is also a parallelogram, and those diagonals bisect each other, okay? So now we're looking for HK. So our goal is to find this HK here. So this is what we're looking for. I'll call that X. Well, what I see already, I can easily see it. We zoom in just to show everybody a little bit more close up, is that this triangle here, the one that includes that HK value, is a right triangle. That means I can use the Pythagorean theorem. So if I have 2 of the sides, which I do, I can find the 3rd side using the Pythagorean theorem. Okay, so Pythagorean theorem, remember, it's a squared plus b squared equals c squared. A and b are the legs. So if we use a squared plus b squared equals c squared, a would be 5 or 12, it doesn't matter, and then b is the other one, so those are the 2 legs, and then the hypotenuse over here is c. Okay, so if we think of it like that, then we can set up our Pythagorean theorem and our equation, right? So 5 squared plus 12 squared is equal to x squared, and remember, x is hk because we're looking for hk. And then 25 plus 144 is equal to x squared. And we get what? 169 is equal to x squared. And then lucky for us, when I square root both sides, I actually get a whole number. So if you square root 169 in the calculator, you do get 13. So 13 is x. Okay, and it wants to know the length of HK. X and HK are the same because that's what we use x for. So we're done. We just need to make sure we have our units and write it with our proper notation. Okay. So it looks like we're going to have inches. So we can have that HK equals 30 inches. Not 30, excuse me, 13 inches. And that's it. All right, example 3. In trapezoid QMNP, MN is parallel to QP. So this means parallel. Measure of angle M is 108, measure of angle P is 4x minus 15, and measure angle Q is 3x plus 21. What is the degree measure of angle N? All right, before anything else, let me underline the fact that it's a trapezoid because that's going to tell me what properties I can use. And then it looks like I'm talking about angle measures. I have some angle measures given, and I'm looking for the degree measure of angle N. Okay, so what do I know about angles and trapezoids? Let's take a look. So trapezoids have the relationship that they have at least one pair of parallel sides, and we know which ones because it told us. And then the adjacent angles between those parallel lines are supplementary, so we know we can use that relationship. Okay, so let's take a look. So the parallel lines, let's go ahead and notate those. MN is parallel to QP. Okay, now let's label all of our angles and see what kind of relationships we can use. So M is 108 degrees. I'm just going to ignore the degrees for now, just to make my figure a little simpler. P is 4x minus 15. And Q is 3x plus 21. And then N is the one we're looking for. So I'll just put a question mark up there. Okay, so it looks like we can use the fact that we have those supplementary angles. So in between these two parallel sides, I have angles that are adjacent. So on the same side, they are supplementary. So for example, 108 and 3x plus 21 are supplementary. So let's go ahead and notate that. So those are supplementary. And the same thing about the other side. And since we have all four angles, it may be helpful to use that relationship twice. We could maybe, right, if you think about it for a second, we could maybe use the fact that it's a quadrilateral and all four angles add to 360. And that may allow us to figure out what N is, but in terms of X, and then that won't really give us the degree measure. So I wouldn't recommend that because then your answer will still have X's in it, and that's not going to help us. So I would do them separately. So what I mean by that is I would work on the left side first over here, because we have 108 and 3x plus 21, and we should be able to solve for X if we create an equation. Okay, so we're going to use the fact that they're supplementary. So 108, excuse me, plus the 3x plus 21. So if I add those two angles together, they're supplementary, so they equal 180. Then I just solve. So I have only one X term. I'll combine these two. So 3x plus 129 is equal to 180. And then I'm just going to solve this equation. So 3x is equal to, I think it's 51. Do it in my calculator so I don't mess up. 180 minus 129. Yeah, 51. And then just divide by 3. And so we will get x equals 17. Okay. But that's not the answer that we really wanted, right? We didn't want x equals 17. We wanted the degree measure. The degree measure of angle N. Okay. But good news, I have the X value. And what I see over here is wherever angle N is, its relationship is supplementary with angle P. And P contains an X. So if I were to take this X value and plug it into P, I'll know what P is in terms of a degree measure, right? And then I can use that supplementary relationship to find N, and I'm done. Okay, so all we need to do is take that X value and we're going to substitute that into angle P. So angle P, I'll just put P equals, just to make it faster, 4 times 17 minus 15. Okay, so let me put that in my calculator. So 4 times 17 is 68 minus 15. And so that's going to be 53 degrees. So that's going to be angle P, 53 degrees. Well, I know that that is supplementary with angle N. So I know that whatever N is plus the 53 degrees is going to give me 180 because they are supplementary. Okay, because they're supplementary, I know that that's what's going to happen. So just subtract 53 from it. You don't even have to really create an equation. You can just do the subtraction. And you will get that angle N, using N for short. So 180 minus 53 is going to be 127. Okay, 127. So the degree measure of angle N, so the measure of angle N is equal to 127 degrees. And we'll find the answer with our correct. All right, perfect. Last but not least, let's look at example 4. So this one's going to be a little bit more complicated. I know this one can be a little bit tricky to think about. It's using coordinate geometry. I'm going to try my best to simplify it as much as possible. So given quadrilateral EFGH with vertices at E, F, G, and H, and it gives you vertices, prove using coordinate geometry that EFGH is a rectangle. So we need to prove this is a rectangle. That means we need to be familiar with the properties of a rectangle. Well, let's look at the definition of a rectangle. So the definition of a rectangle is a parallelogram with 4 right angles. So we need to prove that all of its vertices are right angles, right? That all of its sides intersect at right angles. Well, we also need to sort of explain as well, because this is important. This is like an important part of the properties, is that these opposite sides are congruent as well. Okay, so we need to prove that like these opposite sides are the same, and then the ones on the other two pairs of opposite sides. Okay, the other two pair. Okay, so looking here, let's go ahead and do the diagram first. Let's go and plot these points. So negative 4, 8. That's E up there. Okay, and then F is at 8, 4. 8, 4 is F. Okay, and then G is at 5, negative 5. FG. Okay, and then H is at -7, -1. Okay, and then I'm just going to draw in the sides of our rectangle, or what we're proving is a rectangle. So first things first, we have to prove that all of these vertices are right angles. So how do I prove using coordinate geometry that an angle is a right angle? Well, the only way that we know of is to show that the two lines intersect at right angles, which means they're perpendicular. And the way to show those are perpendicular is that they have opposite reciprocal slopes. So we need to show that the sides have opposite reciprocal slopes. That's what we need to show. We need to show that for all pairs of sides. But because it's a rectangle, you'll see that there's a lot of repetition. So let's go ahead and just look at what the slopes are, and then I'll go over kind of how we can shorten it. So if I want to find the slope, for example, the slope of EH. Okay, so the slope of EH, so rise over run. So I'm just going to do it straight on my diagram. My rise is 1, 2, 3, 4, 5, 6, 7, 8, 9. My run is 1, 2, 3. Okay, so that's going to be 9 over 3, which is also just 3. But I noticed that slope is going to be the exact same for G to F. Okay, so let's just double check here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Okay, so that's the same. So this equals the slope of GF as well. And then hopefully you can see that that's also going to be true when we look at the other two sides, EF and HF. So let's see. So for EF, we go down 4, so -4, and then over 1, I think it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, so that's 12. Okay, so the slope of EF is -4 over 12, which simplifies to -1/3. But again, that's going to be the same slope as HG. Let's just verify. So go down 4, right 12, -4, right 12, and we get the same slope. Okay, so slope of HG. So those slopes are the same, right? The slopes of the two, they're not vertical, but closer to vertical, right? So EH and FG, and then same thing for, so EH and FG, yep, and then EF and HG. Okay, so these, same slope, and then same thing for the other two. So now we can kind of just summarize the fact that those are right angles all at the same time, right? So we can say that EH and EF are perpendicular. And then same thing for HG and GF. And then same thing for EF and FG. But we don't need to write them all out separately. We can say because the slopes are opposite reciprocals, all 4 vertices are going to be right angles. And you have this here to show the slope that you're talking about. Okay, so we can say, since the slopes of each pair of adjacent sides, so adjacent means next to, adjacent sides are opposite reciprocals, all 4 vertices are right angles. Okay. Now, similarly, I guess it's using the same information, but the reasoning is not the same, okay? But using the same kind of information, we can talk about the fact that EH and FG would be the same length, and then EF and HG would be the same length, okay? And that's because of, you can use either the Pythagorean theorem or the distance formula. They're really the same thing. But for example, if I were to use the distance formula to find HG, I would plug in a y change of 4 and an x change of 12. Well, I would do the same y change of 4 and x change of 12 to find EF, meaning that they would have to be congruent to each other because I'm plugging in the same values to the distance formula. And it's that same argument that also works for EH with 9 and 3 and FG with 9 and 3, okay? So we can go ahead and summarize that using the information that's already in the diagram. We don't even need to rewrite it. Okay, so we can use the same information that's in the diagram. So what we can say, let me go ahead and say what we're doing. So opposite sides are congruent because if we plug in the x change and y change, I'll just word it that way, x change and y change to the distance formula, or you can use Pythagorean theorem, it's honestly the same, to the distance formula, we will get the same values. Okay, so the opposite sides are congruent because if we plug in the x change and y change to the distance formula, we will get the same values. And that's true for the opposite sides. So that's true for E, H, and F, G, and you can write that specifically if you'd like. And then that's also true for E, F, and H, G as well. Okay. All right, and that's all you really need to do for that one. So there we go. Thanks for watching, everybody. Have a great day.